All right, ready for problem 4.1, and I wrote the word monopoly problem on here because this is the problem that really has a lot of resemblance to the monopoly problem. So as you're thinking about the monopoly problem, this might be a good place to reference as you think about it. Okay, so this problem, we talk about what we have a probability if it's raining today, then we have a 45% probability it rains tomorrow. Versus if it doesn't rain today, then there's 15% probability it rains tomorrow. Both these probabilities are probably way too high for Lubbock. But okay, well, that's fine. But we do know that it's true that when you're kind of in a rainy cycle, you're more likely to continue the rainy cycle. And when you're in a dry cycle, you're less likely to transfer into a rainy cycle. So notice this kind of gives us the idea of what I meant how we're talking about transitioning from one state to the next state. So let's start this problem just in the most basic way possible, and that is let's just think about our probabilities and see if we can calculate them by hand. Okay, so if it's raining today, today it rained, so it's a 100% chance it rained and a 0% chance it didn't. Well, it actually didn't rain today, but we can pretend, right? We're good at pretending. Then the question is, well, what's going to happen tomorrow? Well, tomorrow, what you'll notice is that because it rained today, there's now a 55% chance that it rains tomorrow. Oh, I wrote the wrong number down on this page. This was 55. Okay, so sorry about that. All right, so because it rains today, there's a 55% chance it rains tomorrow. And that means there's only a 45% chance that it doesn't rain tomorrow. Okay, so that was simple because we know which state we're in. We're now in either 55% chance, 45% chance. But what about the next day? The next day is when it gets interesting because we now have two possibilities. Either it rained again, which means that this would give 55% to the not rain, or a 45% chance of it not raining. So if it rained the next day, then there's a 55% chance it continues to rain and a 45% chance it stops raining. So each of these are probabilities we can calculate. This probability is just 55 times 55. So the probability that you went today, went to this step, and then went to this step is 0.55 times 0.55. And so that ended up being 3.025. So that was that number. 0.3025. 0.0325. And then this one would have been 0.55 times 0.45. So this would have been 0.2475. So there's a 30% chance that it rained tomorrow and continued raining the next day. And then there's a 24% chance that it rained tomorrow but then stopped the next day. But there's another possibility. The other possibility was that you were in this range, in which case you could have began raining or you could have continued not raining. And now, if you're in the not rain state, then there's only a 15% chance that you switch to the rainy state. And if you're in a not rain state, then there's an 85% chance that you continue in the not rainy state. Okay? So that means the probability of being here is 45%, the chance you went here first, times 15%, which turns out to be 0.675, 0.0675, and then so that means you had a 30% chance it was raining because it rained both days, and a 6% chance that it didn't rain and then began raining again. Okay? Versus the probability to get here to go to not raining and stay at not raining is 45 times 85, and that is 0.3825. So that means that on this next day, there was a 24% chance that it rained and then stopped. And then there was a 38% chance that it stopped raining and then continued not raining. And so we can add these together, and that will give us our probabilities for these two ranges. So let me just write these down. So this number, we just add those together, and we get 0.3025 plus 0.0675. And so that means I had a 37% chance that it was raining the next day, And hopefully this turns out to be 63%. Otherwise, I'm a little bit concerned about what's going on. It means there's a possibility to do neither. And I think usually one of the two happens. And it did come out to be 63%. Okay, so what you see is that we had to combine both probabilities. We had to combine the probability that something happened, we were in this state and then switched or stayed the same, or that we were in this state and switched and stayed the same. And then we had to combine those probabilities together. So let's think about this in a little bit more of a theoretical matter. And that is, what if we were in the position where today it was raining or not? Then what's going to happen tomorrow? Well, let's go back through those same two examples. And so we know that we had a 55% chance of going here, and then a 45% chance of going here. Versus if we were in this state, we know we had a 15% chance of going here, and then an 85% chance of going here. So what you'll see is really quickly we can see what our answers are. If we had an X% chance of raining today, then the chance of having rain tomorrow is 0.55x plus 0.15y. And then down here, if we had a Y% chance of not raining today, then we have a 0.45x plus 0.85y% chance of not raining tomorrow. So you see the probability of raining depends on both the probability it's raining today and not raining today. And those two probabilities combine together to give you your new probability. Now, if you're playing along at home, you might say, oh, this is interesting. It's almost like this is a vector, and we got out vector answers. And because we're in linear algebra class, that's exactly how we think about it. And so let's think about what that vector would be. So we want the vector xy, and we want to think, well, if we multiply it, we want the top to be 0.55x plus 15y, and we want the next one to be 0.45x plus 0.85y. And now that gives us, so what matrix would we put right here to multiply in order to do this? Well, notice we get row times column, and so our row is, we just need these two numbers across that top row. So we just need 0.55 here and 0.15 here. And then we do row 2 by column 1 gives us that one, and so this is 0.45 here and 0.85 here. And so you can see that this problem right here is summarized as this matrix multiplication. And so this is what we call a transition matrix. This transition matrix means if you multiply it by whatever state you're in, it gives you the next state. So our transition matrix A means that if you have A times your initial state, and what you're going to get is you're going to get a matrix that is your new state. And so in other words, if you're in a position where it's 100% raining and 0% not raining, you multiply by A and you'll get your now 55% and 45% raining. So it all depends on what your initial state is. You'll get your new state right after this. Let me just take just a second and just define what a transition matrix is so that we can deal with that. So a transition matrix is a matrix A and we put all of our values in here. And so for the value that we just had a second ago is 0.55, 0.45, 0.15, and 0.85. But in general, your transition matrix could be much larger than this. But here's how I kind of think through them. I think of it as having our potential things we came from, and so we have rain here and not rain here. And kind of think of these as the columns, and then we have rain here and not rain here. And the big idea is that this is the from part, and this is the to part. So if you look at this number right here, 85% is the probability of starting with not rain and ending with not rain, versus this 15%, this was the probability you started with not rain and ended with rain. So in general, if I wanted to think of a transition matrix, I could think of my transition matrix and I could build any transition matrix I wanted by just having some sort of problem that looks like this, where I have some sort of square in the middle. And whatever this term is, it's going to be in column I and row J. And then if I write from I to row J, then what this number means is this is a probability of transitioning from row I to state J. So if you're in state I, it's probably going from state I to state J. So as I think about the Monopoly problem, we have this Monopoly board that looks something like this. What I would suggest is that you somehow label your Monopoly board as states. Like you could start a go and be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did I count? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you'd have 12 different states, but notice maybe state 4 is Illinois. So on the fourth column, which is right here, on the fourth column, you would have, if you're at Illinois, you would write down the probabilities of every probability of which one you'd show up. So what's the probability of ending up in Indiana? It might be 1 out of 6 if you roll a 1, you get that. What's probably free parking? 1 out of 6 because you could roll a 2. However, some of them are going to be a little large because if you hit the chance, those probabilities end up adding on to the other one. So you have to be a little bit more careful with your probability. But for example, if this was 4 and we got 1, 2, 3, 4, 5, 6, and this was column 6, you might have something like 1/6, and that's the probability of starting in Illinois, rolling a 6, and getting 1, 2, 3, 4, 5, 6, and ending up in Park Place. So 1/6 might be that probability. And so you would just go through each combination, and so this is going to be time-consuming and painful for you because notice you're going to need to have 6 columns and 6 rows and fill out all the probabilities that go into them. A few things you should note about these probabilities. How can you know if you did them right? Well, it's impossible to know for sure that you did them right. However, one thing you should find is that if you add all of these probabilities, the sum should equal to 1 because this is all of the different places you can go starting in 4, and it's a 100% chance you end up somewhere after you roll 4. So you should have a sum that equals 1 from that column, and each column should add up to 1 when you sum them all. Okay, so that's what a transition matrix is. So the first challenge you're going to have in your problem is going to be creating a transition matrix for your Monopoly problem. For our rain problem, our transition matrix was the matrix 0.55 and 0.15, 0.45, and 0.85. Now, an interesting note is, what if I wanted to answer those questions that were on that I have for exercise 4.1? So if this is our matrix, what's the probability of it raining 2 days from now? Well, I could take this, if it's raining and not raining, if I multiplied that by that, that would give us the probability of it raining the next day. What if I wanted to do it twice? Well, what I would do is I would stick a second matrix. I would have 0.55, 0.15, or 0.15, 0.45, 0.85, and I would take that answer and multiply that answer by the matrix again. Notice, multiplying a matrix more than once, this is the same as squaring a matrix. So what I could have done, and I'll do it right now, what I could have done is I could have taken my matrix, and here it is. Let's see if we can see any of this. And we'll go edit, we'll go 2 by 2, and we'll go 0.55, 0.15, 0.45, 0.85. And so there's my matrix. And instead of just multiplying it, I could square it. So I can just come back out. I could just quit. And I can do matrix a, and then just square it. So raise it to the second power. And notice I get my matrix 3, 7, 6, 7, 2, 1, 2, 9. And then I could take that and multiply it by 1, 0. So that squared is the matrix 3, 7, 6, 3. I think I spoke wrong a second ago. 2, 1, 7, 9 times 1, 0. And this ends up just being 3, 7, 6, 3, which is the same probabilities we got earlier. So that means we did it right when we did this problem. What if we want to ask the next question? What's the probability that it's raining a week from now? Can you guess what we're going to do? That's right, you can guess what we're going to do. What we're going to do is we're just going to raise it to the 7th power, and your calculator is completely capable of doing this. So I'm going to just rewrite this, put 7 instead of 2, and hit my power. And there's my probability, 0.251 and 0.748. What you'll notice, if I multiply it by 0, 1, it's just going to be that first column. It's going to tell us all of my likelihoods. So it ends up that 0.251, 0.251, and 0.749 are going to be my probability. So this is my probability of rain, and this is my probability of not. Okay, why did I look at just the first column? That's worth asking. Well, we could have thought of it as we took our whole matrix and multiplied it by 1, 0, and that would be exactly right. And so then we would have got that column times 1 would give us that first value. That column times 1 would give us that second value. So that's definitely one way you could think of it. But you could also think of it as this matrix has a bunch of values, and after 7 turns, I went from the rain category to the rain category. That's this circle right here. So this circle right here is the from rain to rain category after I've done it 7 times. That very first coordinate means you started raining, you've existed 7 days, and it's still raining. And then this category means you started raining, you've existed 7 days, and it's not raining. So you can see that that column has the from to nature that gives us those 2 values. Okay, now there's one other interesting thing to talk about. And the last interesting thing to talk about is what we call a steady state vector. And a steady state vector is kind of is a little bit what it sounds like. A steady state vector is a vector that whenever you apply it to your matrix, whenever you transition it, it doesn't change. It stays the same. So this is the state. This is a state of probability with rain and not rain, that if you have this probability of rain and this probability of not, and then you apply it by x, the probabilities have stayed the same. So the next day hasn't changed the probability from what it is the day before. So the probabilities stay the same on both sides of the steady state vectors. Okay, well, how do we do a problem like this? The answer is we do a little bit of algebra. And so I'm going to subtract x over to the other side, and I'll get ax minus x is equal to 0. I need to think of that 0 as a 0 vector. And now I'm going to factor the x out. You have to factor to the right. And so if I factor the x out, what do I have left? I have a minus 1. That looks weird. How do you subtract a number from a matrix? The answer is this isn't a 1. It is a matrix version of 1. So it's a minus the identity. And so all I'm really trying to do is I'm really just solving this equation. And if I solve that equation, that's what tells me what that steady state vector is. So let's find the steady state vector for our problem. The steady state vector for our problem is, we get 0.55, 0.45, 0.15, 0.85, and then we minus the identity from it, and we want that times x equals 0. So this is a homogeneous problem. We do all of our subtraction. What you'll find is that 0.55 minus 1, we've got a negative 0.45, 0.45, that, and then 0.15, and then when you subtract 1, you get a negative 0.85, x equals 0. This means we're solving the equation 0.45, negative 0.45, 0.15, 0, 0, 0.45, 0.85, and now this row reduces. You can kind of see already how it's going to row reduce. How is it going to row reduce? You can kind of already see how it's going to row reduce, and that is if you just add the two rows together, the second one's going to become completely 0. So we get negative 0.45, 0.150, and then our next row gets 0, 0, 0. Now we're going to have lots and lots of solutions to this. So if you look at this first one, that means negative 0.45x plus 0.15y equals 0. Let's solve it for x. And so now notice x is 1/3 of y. So you get negative 0.15 divided by negative 0.45. So x equals 1/3 of y. This gives us our solution set. So our solution set is xy. X is equal to 1/3 of y, and y is equal to 1. Y. That's interesting. So if I wanted to make this into a real solution, I'd have to think about it a little bit. And the way I would think about it is I need, because if I want a solution that actually makes sense for the rain problem, it doesn't make sense to say it's raining 1/3 of the time and not raining 100% of the time. That doesn't make sense. So what I need is these to sum to 1. Right now, the sum is equal to 4/3. So a way that I can sum to 1 is I can just make y equal to 3/4, and that will make the problem all work out nicely. So I'm going through a lot of whiteboards here, but that's perfectly fine. So now as I look at this, what you'll find is that if I let y equal 4/3, then my sum of these two will be the exact opposite of what I want. Oh, wait, if I make y equal to 3/4, then they'll sum. Because notice these sum to 1/3 to 4/3, so I make that the reciprocal, and therefore they'll sum to 1. So if y equals 4/3, then what is xy equal to? It's equal to 3/4 times 1/3, and that becomes a 1/4. 3/4 times 1 and 3/4, or 0.25, 0.75. And so you can see that if it rains, if I predict that it's going to rain 25% of the time and not rain 75% of the time, then when I multiply that, I get the exact same answer. So in other words, if I take my original matrix, 0.55, 0.45, 0.15, 0.85, and multiply it by 0.25, 0.75, what I get out is 0.25 and 0.75. Now what's interesting is if you look at this answer, you'll notice this is actually pretty similar to what we got when we did the 7 days later problem. And the truth is that what a steady state vector is telling us in practical terms is this is the long run behavior. So if you were to predict what's going to happen 100 days later, well, what happens today doesn't really matter because it's been washed out by all the probability that's happened between now and then. And what you find is that over time, you trend towards this steady state vector. And this 0.25, 0.75, that means that 3 years from here, 5 years from here, there's a 25% chance of it raining, 75% chance of it not raining. Definitely not true for Lubbock. But notice we could look at this by looking at our matrix. And so if I took our matrix and instead of raising it to the 7th, I raise it to, let's do 700. Is this going to break my calculator? It might. Let's give it a go, though. Oh, it did. It didn't like it. Okay, so I think it got too big. So let's go let's raise it to 100. There we go. And notice that when you hit 100%, you've got 25, 75, 25, 75. So it's completely, all the decimals have disappeared and it's rounded it to our steady state vector. So in some ways, the steady state vector is telling you what's happening in the long run. So for this monopoly problem, I asked the question of which Which square are you most likely to find yourself in the long run? What should you do? Well, you need to create a steady state vector. And that steady state vector tells you if you've played the game over and over and over again, you're in one of these typical like 3-hour Monopoly adventures with your friends and you'll hate each other. At that point, which square are you most likely to be on? The answer is given in the steady state vector. So you look down the steady state vector, whichever numbers are the highest, those are the ones that you are most likely to be on. Those have the highest probability. By the way, if you're curious about playing Monopoly just yourself against your friends, it's the orange squares. Indiana, Illinois, the orange squares right up here are the ones that are have the highest value because they're the highest numbers on a steady state vector for a full 10 by 10 by 10. Oh, I think it's 12 by 12 grid of Monopoly. By the way, if you want to, you could go do that. That'd be a fun project. Take a full 12 by 12 Monopoly board, put all the chance cards and everything into it. Get yourself a nice, gigantic, like 48 or something square, 48 by 48 chain matrix and solve it. I would be really impressed. I haven't had a student take me up on that. So, but maybe since you all are at home and quarantined, you'll say, hey, I could spend a day analyzing Monopoly and figure out the probabilities that go with each square. And this is how you would do it. You would use a Markov chain. All right. Well, hopefully you can get started on the Monopoly problem. It's hard. It's a challenging problem, and I know that. So definitely come to my study hall hours, and I'll work with you and talk to each other. So get linked up with some of the other students. You can do that at study hall. You can do that outside of study hall and work together on this. I want you all to do a really good job of this application problem and then give it to me when you're all done.